So next we have Jarno Rantaharju, who's going to tell us about vectorization and parallelization in modern CPUs.
Okay, thank you. So yeah, I'll talk a bit about, as you said, getting to a bit of a more technical part of the program, I guess. Not about really or less about science and more about the HPC infrastructure or how to use it well, right? So just to start with, there's some context of how the processes have been developing in the recent years and going back a few decades. And the main point here for this talk is that essentially the development of the frequency of the clock frequency of the processors has stopped about 10 years ago. So that's this green data points here. Essentially, the processors haven't gotten any faster in 10 years, right? Actually, it's slightly gone down, right? This is a log plot, so you don't see that well, okay? Now, the reason for that is possibly familiar. When you try to increase the clock rate, you increase heat production and you need to get rid of that heat or your processor will melt, right? That's not a good thing. Okay, so it gets harder and harder when the transistors get smaller to dissipate that heat because the area decreases and the gates themselves become narrower. So you produce, that means two things. You produce more heat because the current is going through a narrower piece of metal or a conductor. It also means that you have less area to dissipate heat. Okay, so it's getting processors to run faster has been a really hard technical challenge, and it's getting harder. Okay, now so the solution essentially, well, one of the things that has continued, as you can see, is the transistors have become smaller, and on a standard CPU, the number of transistors is still scaling linearly in this log plot, so you're still following this exponential scaling law that has been true for a long time. And well, how is that useful then? Well, if you can't make the clock rate go up, you can use the transistors to do more operations at the same time, right? Okay. And that's how we get to vectorization. So the problem goes from people creating processors that run your things faster to you writing programs that actually use all of the processor, because it's slightly harder to make them general purpose, right? Okay. There's some other interesting features there that you can take a look at, either the original data or read out from there, but I'm not going to go too much into that. But essentially, you want to use those. You want to use those transistors, and that means you want to essentially build more cores out of those on that core that CPU, right? One way to do that is to just put multiple cores there, and you have all been seeing that the number of cores on the processors keeps increasing. You have something like 40 cores, or you have 40 cores on the current, the new cluster that you will start using soon. And that's a relatively straightforward solution, in that you can just run more things on those essentially separate CPUs. It enables you to do more computation while actually generating less heat and using less power. But it does add to programming complexity. So you have to essentially take care of, you have to write a program that uses all of those cores at the same time, and you have to take care of the fact that they don't actually share data on the CPU itself, on the processor itself. So that's they do share memory, right? So they share some cache levels depending on the processor, but they don't share all the memory. So you have to essentially manage some of the memory access, right? Okay, that's one way of doing it, and that's relatively straightforward to program for in the end. But it's not necessarily the best way of doing it in all cases. So the other option that makes things harder for us is vectorization, right? That means that instead of just copying the whole of the processing unit and placing more than one on one chip, you only copy some parts, essentially. You copy the computational units and the part that loads the data, the load store units. Okay. And you have them all do the same instructions. So you have one scheduler, you have the scheduler gave it one instruction, and they all do the same thing, right? That means you are copying only a smaller part of the processor, and you're saving space. You're using only this one instruction manager that exists on the chip, and you're still doing twice as many computations, or 4 times as many computations, or 8 times as many computations. They just all have to be doing the same instruction. They all have to be doing the same thing. Okay. This is significantly harder, of course, to code for. You can't just have them do whatever you want. You have to somehow order your computations so that they can all be doing the same instruction at the same time. Okay. Now, well, nevertheless, this saves a lot of space. It enables essentially you to do a lot more computation. So all the major manufacturers are going hard into this direction. Right now, the standard is 8 floating point operations at the same time. Right? That's, depending on who you ask, that's AVX2 or scalable vector with 8 floats. The ones on Sunbird will have 16 floats. That's the Intel's new standard, AVX 512. And so most of you will be trying to take advantage of that. Either if you're not doing that yet, then relatively soon. Okay, thanks. So how do you do that? Okay, the easy way first. You can try to get the compiler to do what you want. So if you just tell GCC to use these instructions, or if you're running ACC, you use that directive and you ask it to actually tune for Skylake. It will try to make use of these instructions with the program that you have written where you didn't probably think about vectors. Okay. You can also make it print out what is happening and hope that everything goes well. So here's a nice simple example. It's a very simple data structure. You just have 2 numbers. You're accessing them in order. Everything seems fine. You're doing a loop that's pretty big. It should be able to handle this. But the compiler actually can't. It doesn't know everything, and doesn't really know. It knows a lot less than you think. It's written by a person, and that person didn't know your code when they wrote the compiler, right? So you get some feedback from the compiler. Essentially, it's telling you, I can't vectorize this. There is this easy solution, actually. Now, for this simple code, you just add this thing, this pragma, in front of the loop, and it works. You have to compile with -f OpenMP on GCC, for example. Okay. And this is probably the solution that is going to be the most straightforward to implement. You probably may have to restructure your loops a little bit, but try it out, see what happens. It's relatively straightforward. If it doesn't work, another way of doing it is to try to restructure your data, to reorder the data in such a way that the loops are, or the vectors are really straightforward, that it's really clear. So here there's just a simple data structure. It's just one float, one float, one float. You always add them in order. Okay. You make it really obvious, right? Then the compiler can figure it out. Okay. Now, something I've been working on with this OpenQCD is to really take the advantage of all of the instructions in the best possible way by telling the compiler by hand what you want it to do, right? And that can be done using these intrinsic instructions. So this actually is a function that tells the compiler that what you want. Thanks for it. What you want it to do is to take 8 numbers, add those 8 numbers together, and produce the resulting 8 numbers into this variable. Okay, right? And this, of course, gets vectorized perfectly. Okay, actually, just as well as the OMP one. So that's probably the one you want to check out first, if you haven't already. Okay. So not going too much into this. This is not the best possible example for a code to vectorize because it is memory bound rather than compute bound. But if you ignore the memory dependencies, you get what you expect, about double the speed of what you get if you just run the AVX2. Okay. And that's achieved in this case using the intrinsic operation. So just actually really telling the compiler very carefully what to do, right? Okay. If you do the full program, you get a lot less. But what you do see is that you still get an improvement. So even if you know that your program is not actually bound by the number of computations you can do, it's actually bound by memory, you can still access a whole vector at a time instead of just accessing one number at a time, and that makes it a lot faster. This is just a 10% improvement, more or less, but it makes a difference. Okay. All right. So that's essentially my point. Is the first thing. Trends suggest that vectors will grow. You will see more cores per processor, bigger vectors on the cores. And that's because the clock speeds have been stagnant and there's no breakthrough at the moment, no technical solution for the heat problem. But transistors can get smaller, and therefore you can do less computations, more computations with less energy as the technology develops. Okay. You just have to go through a bit more effort to write programs that are able to do things at the same time instead of sequentially. And there's nice tools for that.
Thanks, speaker. Any questions?
Is it normally pretty problem specific when it's worthwhile to do, or is it pretty generally going to be a good idea?
Well, I would say that it's generally a good idea to at least let the compiler do as much work as you can. And OMP is probably a good idea to put in there, just to see if there's something you can actually vectorize in the code. But it depends on if you are bound by memory or if you're bound by computation.
Anyone else? Any other questions? Right, can we thank the speaker once more?